Hello, everyone. We have convened here today to listen to Dr. Debmalya Panigrahi. Let me introduce our speaker first. And before that, I'll introduce myself very briefly. I am Arghya Bhattacharya. Dr. Devargo Sharkar and I, both of us, we are a part of the administrative committee of JB Scholars Professional Development Forum. I am a scholar of 2012 and I am currently pursuing my PhD in computer science from Stony Brook University, which is in New York. Our speaker for today, Dr. Debmalya Panigrahi, is a JB Scholar of 2000. He is an associate professor of computer science at Duke University. He did his undergrad from Jadavpur University and master's from IISc Bangalore. He was a gold medalist in both places. He did his PhD from MIT. His research is on theoretical computer science, and I request him to enlighten us a little bit on his research at some point in this talk. His research has found tremendous real-world applications in database, computer networks, and internet search and advertising. Regarding the logistics of this talk, you can put your questions in the chat if you want, or you can ask yourself. We will open for a Q&A at the end of the talk. That's it. Let's welcome our speaker, Dr. Panigrahi. See you.
Okay, all right. Thanks, Arghya. That was a generous introduction, and thanks a lot to the organizers for giving me the opportunity to speak to this audience. It's not every day that you get a chance to speak to a broader spectrum of scientists. We tend to get ourselves pigeonholed into small areas, and we just keep talking to our peers. So this is an excellent opportunity for me to, in some sense, evangelize for my scientific community, but also to kind of reach out to many of you and talk to this broader spectrum of scientists. So thanks for that opportunity, and thanks
It's our
to
pleasure.
thank you, and also thanks a lot to all of you who are here today to hear this talk, particularly if there are others. I know Arghya and Devargo are certainly in the US. There might be others who are also in the States. Many thanks to them for waking up early and coming to this talk. So let me share my screen. In terms of the format of the talk, what I'm going to do is I'm going to speak for somewhere around an hour, probably a little less, on a particular topic that I'm going to discuss next. But after that, I'm going to open the floor and take questions. And these questions need not have anything to do with the talk itself. So feel free to ask me any questions about anything that you think I might have the answer to, whether that's about science, or that's about your career, or anything else. So there will be a phase where I'll open the floor to questions. And also, finally, before I start, I want to say that I will, just by the nature of this talk, I will sometimes step out and talk about things that I'm certainly not an expert in. I'll maybe very briefly talk about physics. I'll very briefly talk about biology. I will quite extensively talk about some parts of mathematics. Not all of these things are certainly not things I'm an expert in. So, and many of you are probably know a lot more about some of these things than I do. But part of the reason that I'm going to talk about all of these things is to provoke you, and I want you to be provoked. So if you feel that there's something that you want to contest, and that's the way you should do it. So you should just protest anything that doesn't feel right. Okay, so and I also want this to be a conversation rather than a talk. So I essentially put together the slides yesterday. Well, not essentially, actually put together the slides yesterday. So so it's not going to be me giving a pulpit lecture. I want this more to be a conversation between us. So I do want you to ask questions during the talk if you have any. Okay, so with that, let me start. I do have a fairly provocative title. So I'm asking, is computer science a basic science? These are the kinds of things there's no clear answer, whether it's yes or no, but I will make an argument for the case that it is. And I'll make this argument through some puzzles, paradoxes, and problems. So let's start off by asking what makes a science basic. And there are many answers to this question. You can come up with all kinds of desiderata that makes a science a basic sort of intellectual pursuit. But I will explore this question along two specific axes today. And the first is what I call being fundamental. Now, I haven't really done anything when I say that it's something that's basic is also fundamental, right? I've just replaced the word basic by fundamental. But what I mean by that, in a nutshell, is that it's a science that reveals some of nature's hidden secrets. Okay, so something that has very easy questions, but not so easy answers. Okay, so very elusive answers for questions that you could ask without knowing something like things specific to that particular area. Okay, so that's the kind of thing where that's the kind of thing I think of as being a nature secret that's hidden, and this particular discipline, this particular science is trying to unravel that secret. So that's one of the axes that I'm going to explore. And the other axis that I'm going to explore is of being universal. Okay, so as scientists, we often have this quest for the ultimate explanation. Okay, one answer that resolves a lot of questions. And that's the second lens that I will see computer science through. So does it aspire to develop these ultimate explanations for phenomena? Okay, because that's the way that science over the last 500 years, over many centuries, has progressed. So these are the sort of my two theses. These are the two axes I am going to explore today. So let's start off. Let's start talking about being fundamental. So before I even talk about computer science and why I think it is fundamental, let's try to understand this a little better by a few examples from other areas that incontroversially are basic sciences. So for example, in mathematics, let's consider the following question. So take any even number larger than 4. So among all even numbers, we're excluding 2 and 4. Now, any even number larger than 4 is the sum of 2 primes. So this is a conjecture, and this is known as Goldbach's conjecture, because this was first stated by Goldbach in a letter to Leonard Euler in the 18th century. It's a long time back, more than 250 years back. And amazingly, this conjecture that makes sense even to a high school student, essentially all you need to know is what is a prime number, right? And then you know what this conjecture is. But this conjecture remains open, perhaps the biggest open problem or one of the biggest open problems in mathematics. So again, an extremely easy question, easy to state, easy to understand, but an elusive answer. We don't know how to solve this. Let's think about physics, and here's a conjecture from physics now. This is called the arrow of time, first proposed by Arthur Eddington in 1927. So this says, does reversing time change the laws of physics? Okay, so what that means is that in our conscience we have this idea that time is asymmetric, that it goes from the past to the future. And this asymmetry does seem to be wedded into certain macroscopic physical phenomena. On the other hand, if you look at a lot of microscopic phenomena, they seem to be reversible in the sense that the phenomenon does not change the laws that govern the phenomenon. That doesn't change if I reverse the direction of time. So is this direction of time fundamental to physical laws or is it not? And there seems to be some, there doesn't seem to be a single answer to that yet. Okay, so another question that's completely open. Again, simple question, not such an easy answer. And finally, from biology, there is this ultimate question: How did life originate? So, and this question has bugged humanity for many years. Even Aristotle, here in like 300 years before the birth of Christ, did ponder on this, and the Greek philosophers and Greek science. I mean, in those days, a lot of philosophers were also scientists, and so they pondered on this from a somewhat philosophical angle. Uh, and then this kind of came back into prominence when once Darwin came up with his theory of evolution. So evolution is a very apt theory in explaining how life transformed over time, uh, but it doesn't quite explain how life originates, and that remains perhaps the sort of biggest prize in biology, the biggest question in biology that we don't have an answer to. Again, extremely simple question. So did it originate from non? Did it originate via chemical processes on things that we generally think of as non-living, or what happened? So those are the kinds of questions that we think of as fundamental. And although we can't quite define what fundamental, like what being fundamental means precisely, intuitively, I I hope many of us agree that these seem very fundamental things to think about as an intellectual exercise. So does computer science offer that kind of intellectual fodder is what we are going to see. And our story today goes back to 18th century Germany in the day, to the city of Königsberg. Today it's in Russia, it's called Kaliningrad. And what was special about the city was that its map had this peculiarity that there were four different land masses. So there were two islands and two banks of a river, and there were seven bridges between these land masses. That was how the city was laid out. And someone came up with this question that became quite famous in the day. So is there a walking route in the city, or a walking tour route in the city that crosses every bridge exactly once? So can you start at some location in the city, cross every bridge exactly once, and come back to that location? Very natural question if you think about it, but one that people thought about and didn't quite have an answer to. Now, this question certainly is not open. We do have an answer to this question, and the person who solved this was Leonard Euler, uh, one of the greatest, if not the greatest, mathematicians of all time. And the way he solved it was by abstracting this question into something on an object called graphs. So I'll very briefly talk about what that means. So think of the following. So think of every landmass and replace every landmass by one of these single blue circles. Okay, these things are called vertices. Now take each bridge and draw a line between any two circles, any two of these vertices, if the bridge connects those two landmasses. Okay, and then what you get is this thing that I've drawn on the right. This is usually called a graph. Okay, so this exactly represents the map as to the level of detail that we needed, right? So we don't really need details of where the roads are and things like this, but we do need to know which bridges connect which pairs of land masses. And that's exactly what this graph that represents the map of the city captures. So once you have done this, then you can kind of think of this question more abstractly, and you can ask, can I actually do a tour of this graph? Can I actually walk on the edges of the graph in a way such that I I traverse every edge exactly once. Remember, the edges are bridges, the dots or the circles are land masses. So really, I'm trying to take a tour of this graph such that I traverse every edge exactly once. And Euler realized that's not possible. Why is that not possible? So look at this vertex, this circle on the right. So this circle has three lines going into it, three edges going into it. Now, if I were able to do this, if I were able to come up with such a tour, then of every time I visit that vertex, every time I go to that landmass, I need to also exit that landmass and go on to my next stop. But I can't do this since there are three edges. I can't do this. I can't do this precisely in this graph. Like the first time I visit, I'll use up one of my edges. I leave, I use up a second edge, then I'm left with one edge. So if I want to visit a third time, then I won't be able to leave. I will get stuck at that location. Okay, so that was Euler's reasoning behind saying that look, the problem that the townspeople of Königsberg came up with is not solvable. Okay, and his reasoning was that there is this vertex that has an odd number of edges going into it. If you have that structure, then it's not possible to come up with the kind of walk that you're talking about. But what's more interesting, perhaps, than the solution itself is the following quote by Euler. So he says, as far as the problem of Königsberg is concerned, it can be solved by making an exhaustive list of possible routes and then finding whether or not any route satisfies the conditions of the problem. So what he's saying is, okay, so one way of solving the problem is let me try to figure out what are all the tours that the city allows, right? All the different sequences in which I can walk on the bridges, all the different sequences in which I can visit these land masses. So I can come up with this list. It's an exhaustive list. But Euler also realized that because of the number of possibilities, this method of solution would be too difficult and laborious. And in other problems with more bridges, it would be impossible. So what is he saying? He's saying that it's not enough to solve a problem, at least in this context. We need to solve it efficiently. Because if you just solved this problem, if you just asked for a solution to this problem, there is a solution where you kind of draw every possible tour and figure out if there's any one that satisfies the conditions you're looking for. But that's extremely laborious and essentially impossible if you have a larger city with more bridges, for instance. Okay, and in fact, we will give an example later where it is practically impossible. So Euler was already aware of this role of efficiency in solving problems, a role that we are going to talk about quite a lot on in the next few minutes. So that kind of is a good segue to a question that computer science asks and is at the heart of computer science. So the question is, which problems can we solve efficiently? Okay. Now, also we will ask later on in the talk, we will ask which problems can be solved at all, right? So we will have these sort of two different questions that we will talk about at different points. And it's important to understand the difference. So the first one is saying, all right, so I have some problems like the one that Euler tried to solve, and I have some solution that kind of immediately pops out, right? The solution of actually finding all possible walking tours and figuring out if any one of them satisfies the conditions you want. But that solution doesn't seem efficient. So which are the problems that are solvable efficiently and which are not? And the second thing asks, so if I don't care about efficiency at all, is every problem in the world solvable? Right? So is it the case that really the only thing that we really need to be clever about in a solution is efficiency? If we didn't care about that, then everything's done. Okay, so and we'll ponder on both of these questions today. So what are efficient solutions? So let's talk about the question of efficiency first. So that immediately asks what are efficient solutions, and there is no one easy solution or one easy definition, because efficiency in general is highly contextual, right? What might be efficient on my laptop may not be efficient on my phone, and what might be, let's say, inefficient on my laptop may be efficient in cluster computing or some, like if you use a much more powerful computer. So efficiency in general is contextual, but some solutions are inefficient. Okay, so for example, the solution Euler warned against, the solution of enumerating all these possible walking tours of Königsberg and figuring out if there was a tour that traversed every bridge once, that solution is inefficient. And this statement doesn't have anything to do with the context. So why are we saying so? So think of this. So Pittsburgh has 446 bridges. So it's a more modern city than Königsberg. It has more bridges. How many walking tours do I have? About 2 raised to 446. So why that's the case? Let's not worry so much. It's pretty easy to see that that's a rough estimate of how many walking tours you would have. Now, how long would that take to list on today's computers? So if we actually go listing one tour after another and trying to figure out if Pittsburgh does have a tour that traverses every bridge exactly once, how long would it take? About 2 raised to 400 years. 2 raised to 400. Okay, so to give you some context, 2 raised to 10 is about 1,000. Okay, and really large numbers, like a billion, are still less than 2 raised to 20. Actually, even a trillion is less than 2 raised to 20. And we are talking about 2 raised to 400. Okay, so there is no hope in the world that this can be solved by any computer in the world, leave alone any human being, right? So that solution certainly is inefficient. You don't need to know the context to say that this is an inefficient solution. And that is what computer scientists log on to. So the mantra in computer science is to say, solve problems in polynomial time. Okay, and in computer science, we always say that what's efficient? Anything that is polynomial time is efficient. Okay, so that kind of immediately raises the question, why are we insisting on polynomials? Okay, so if I give you some number n, is n raised to 100 smaller or 2 raised to n smaller? And of course, if you try this out, like try it out on a small number, like 2, n equals 2, 2 raised to 100, which is n raised to 100, is much, much bigger than 2 raised to 2. But the problem is that the term on the left, n raised to 100, which is a polynomial, that grows very slowly, right? So if I keep increasing n, if I change 2 to 2000, this will still be reasonably similar to how 2 raised to 100 looked, right? N equals 2 and n equals 10,000 are not very different if you think of n raised to 100. On the other hand, 2 raised to n looks very different between n equals 2 and n equals 1,000. Okay, so 2 raised to n grows very, very fast. And this is often called the curse of exponentiation. So that's why we want to avoid it. We want to stay with polynomials. And this has served us very well over the years. Okay, so assuming we define efficiency as polynomial, let's try to understand Königsberg's puzzle a little more. So suppose the answer to Königsberg puzzle was yes. Okay, so we saw that the answer is no. There was this landmass that had 3 different bridges adjacent to it, so you couldn't actually design a tour in the city that traversed every bridge once. But suppose it was yes. Suppose you did have such a tour. How would you have solved it then? Well, in that case, Euler had a better way to convince you that he had a tour by just producing a tour, right? If he somehow came up with a tour that actually traversed every bridge once, he could have just said, look, here's my tour. So I have solved your problem. I have shown you that there is indeed a tour that traverses every bridge once. But then that still leaves the question, how does it go about computing the solution in the first place? Okay, so it seems much easier to demonstrate to you that the solution is yes, or what the solution is, in the case that the solution is yes. But it's still not clear how you would have come up with that solution, that example that demonstrates that your answer is yes. Now, of course, contrast this to the other case where the answer is no, the case that Euler actually faced, that there was no tour. Now, in that case, there's no easy demonstration either. As Euler already realized, one demonstration is to list every possible tour and convince you that he has listed every tour, and then say that, look, none of these has the properties that you desire. But that's not an efficient way to demonstrate the correctness of the solution. So in one case, if the answer was no, we don't know how to even demonstrate the answer. In the other case, if the answer was yes, then we do know how to demonstrate it by just producing the answer, but we don't know how to come up with the answer in the first place. Okay, so there is a subtle difference between these two cases, and this turns out to be very important. So this difference between demonstrating a solution and convincing you that the solution is correct versus trying to search for the solution in the first place is what we call the verification versus search question. Okay, so take any problem in the world that you care about, and you can ask this question: if we can verify a solution, so suppose someone comes to you and says, look, I have found a solution to your problem. So now you want to look at that proof or of what the person is giving you, and you would try to verify if the person has actually solved the problem or not. But suppose you can. So suppose you can verify a solution. Does that mean that you can also find a solution? So is there a difference between verification and search? Now, to make this a little more precise, is there a difference between efficient verification and efficient search? So if you don't care about efficiency, then the first question is kind of ill-formed, because if we can verify a solution, the solution does exist. And if the solution does exist, and I have like all the power in my world, I'm not limited in any way, then anything that exists, I have access to. So the first question is slightly ill-formed. So to make it a little more well-formed, we put in this notion of efficiency. So if you can verify a solution efficiently, and you can think of efficiently as quickly, is it also the case that I could have found the solution efficiently? And in particular, in computer science terms, if we can verify a solution in polynomial time, then can we also find it in polynomial time? Now, that's a question that has driven computer science for years. Okay, and some of you might have already heard of this question. So this is a question called the P versus NP problem. This was first proposed by Stephen Cook and Leonid Levin in 1971. Hasn't yet been resolved, and by some distance is the most important problem in computer science. And as I said earlier, this asks this very natural question, very simple to ask question. So if I can verify proofs that you give me, if I can verify solutions that you give me, can I find them in the first place? Okay, simple question, seems to be an extremely difficult answer. Now, why do we care so much about this problem? So what if P were equal to NP? So let me give you a little bit of context. So almost everyone, not everyone, but almost everyone believes that P and NP are not equal. Okay, so these two things are different. Verifying a solution is much easier than coming up with a solution. You can think of it as maybe if some of you are still students and you're taking an exam, is the job of the grader the same as the job of the person taking the exam? So you can think of the job of the grader as one of verifying whatever solution the examinee wrote, whereas the job of the examinee is to come up with the solution. So do they have the same, are their tasks of the same nature of difficulty? That's what we are asking here. And most people believe that it is not. But what if it were equal? What would happen? Why do we care so much? So here's a quote from Volker Strassen. So it says that the consequences, so consequences of P being equal to NP, are so grotesque that their status, so when he says their status, he means the status of this conjecture that P is not equal to NP. So their status may perhaps be compared to physical laws rather than that of ordinary mathematical conjectures. So for most mathematical conjectures, no matter how deep or how natural or how important, most mathematical conjectures are fairly limited in impact. Right? So for example, if Goldbach's conjecture is not true, if there is a large even number that cannot be split into two primes, that will have consequences, but not earth-shattering consequences. The consequences would be limited. So on the other hand, if you think of, let's say, an alternate universe where there was no gravity, then the consequences would be earth-shattering. So Strassen here is saying that really the consequences of this P versus NP question are more at the level of physical laws being violated, more at the level of a completely different world where physical laws didn't hold, than at the level of mathematical conjectures, typical mathematical conjectures not holding. And this would indeed have many practical implications. Probably the most serious being that secure communication in the way that we know it today. So for example, online financial transactions that many of you might be doing, these kinds of things would cease to exist. So clearly deep practical impact. But what perhaps is more intellectually fundamental is that it will signal what people call the demise of creativity. So think of this. So what is this saying? If P equals NP, it's saying that if there's a short proof, so if there's an efficient proof, if there's an efficient solution, now if there's a short proof to a question, then it can be found automatically. There's a computer algorithm that can find every short proof out there in the world. You feed it the statement that you're trying to prove, it will spit out the proof, as long as the proof is efficient, as long as it's short, right? So if a short proof exists, then it can be found automatically. Now, how important is this restriction that the proof is short? I claim it's not particularly important. So if the proof were so long that a computer algorithm cannot spit it out, how do you even expect a human being to spit that out? Right? So if a proof, for example, is more than 1 billion lines long, how is a human being ever going to write that proof? So in a sense, all human proofs in history are short just by the fact that human beings are limited. So this would mean that I don't need any human intervention to do any proofs. I don't need any human intervention anymore to solve any problems. What human beings can do, computers can do better. That would be the crux of what would happen if P were equal to NP. So it wouldn't make any difference if someone's creative, if someone's intelligent, if someone's can come up with sort of beautiful ideas. None of this would matter anymore, right? Because there would be this all-powerful computer algorithm sitting around that just keeps spitting out everything that you want to solve. And in fact, this is not something that computer scientists or mathematicians have suddenly realized. As long back as in 1956, Kurt Gödel, one of the best, like one of the most famous logicians of all time, in a letter to John von Neumann, perhaps one of the most intelligent people who ever lived, writes this. He says, it would certainly indicate that the mental effort of mathematicians could be completely replaced by machines. And he's saying this in the context of what would happen if this P versus NP question were resolved in the affirmative. Okay, so mathematicians would basically be out of a job. And not just mathematicians, pretty much every scientist would be out of a job. So indeed, the consequences are grotesque. So that kind of brings us to this question of where are these hard problems we are talking about? So we are saying that, well, we believe that there are these really hard problems that you can efficiently verify solutions to, but you can't really find solutions. So where are these problems? We still haven't encountered one of them. And in this context, there's this beautiful quote by George Polya saying So Polya, by the way, was one of the greatest combinatorists of the 20th century. So Polya says, if there's a problem you can't solve, then there's also one that you can solve. So go find it. Okay, so this for some of you who are students and starting off your careers. This is beautiful advice. So if you can't solve a problem, don't get disheartened. Certainly there's one for you. There's one that no one else has solved, and you would be able to. But let's turn this on the head. So what's also true, if there's a problem you can solve, then there's always one you can't solve. Okay, so and we are searching for hard problems, so let's try to find it. Find a problem that you can't solve that's similar to a problem that you can solve. And we've already seen one problem that we can solve, the problem that Euler solved. And this problem is the one of the bridges of Königsberg. So now let's change this question ever so slightly. So the question was, is there a walking route that traverses every bridge, that crosses every bridge exactly once? Let's slightly change it and ask, now, is there a walking route that crosses every island exactly once? So when I say island, I mean landmass. So also the two banks of the river as well as the islands. So I'm asking almost the same question. I want a walking route on the bridge on the map of Königsberg. But this walking route now, I want it to have a slightly different property, that I don't care about bridges anymore. I do care about traversing or crossing or walking on every landmass in this map exactly once. Okay, so in terms of this graph that I talked about earlier we were asking for a route on this map, a walking route on this map, or a tour on this map that crosses every edge, every line on this map exactly once. Now I don't care about the lines anymore. I want to make sure that I touch each of these circles, these dots, exactly once. And of course, the answer in this particular map is clearly yes, right? You can take a diamond. There are several diamonds in the map that you can see. You can take a diamond, and the diamond will give you such a tour. Okay, it doesn't cross every bridge, but it does touch every landmass exactly once. So that's the question, and that's kind of brings us to 19th century Ireland from 17th century Germany, and to the Irish mathematician and physicist William Rowan Hamilton. So he invented a game called the Icosian Game. So what was this game? So the objective of this game was the following. So you're given a dodecahedron. So what's a dodecahedron? It's just a geometric three-dimensional structure that has 12 faces. And we'll see an example later. But some geometric structure, some three-dimensional structure. Okay. So you're given such a three-dimensional structure that has edges and faces. And now what he asks is, can I walk along the edges of this three-dimensional body that I gave you, such that I visit every corner of this body exactly once? Okay. Now his game was slightly more complicated. There were two players instead of one player, and the two players kind of collaborated in trying to find this kind of a walk along the edges of this dodecahedron. But let's simplify it, and let's just ask the question for a single player. Can I just walk along the edges such that I visit each of the corners exactly once? Now, not surprisingly, the game was a commercial failure and just too complicated for anyone to play. However, it did give computer science one of its iconic hard problems. So remember, we are searching for our hard problems, and it does give us one of our famous hard problems. And in honor of Hamilton, that problem is called the Hamiltonian cycle problem. So here's the problem. So I have shown you the dodecahedron on the left. Okay, so again, what is this? This is a three-dimensional structure. I've tried to draw it in 2 dimensions. And the structure is such that there are 12 different faces. And now the object of the game is to walk along the edges. So you can see that there is this red path marked out, which is walking along the edges. And you want to visit every vertex exactly once. You want to start at one of the corners of this three-dimensional structure. You want to end at that corner, And in between that, along the walk, you want to visit every corner once, exactly once. Okay. And again, if you think about this for a second, you'll realize that the abstraction to this problem, although the problem as stated looks very different from the problem that people in Königsberg were asking, the abstraction is exactly the same. Okay, so what can I do? I can take these corners. I can then draw the edges between the corners, and that creates a graph for me. I don't really care about these faces and things like this. That doesn't matter in terms of the problem that I'm trying to solve. And once I have this graph, the one I've drawn on the right, then I'm asking, can I now walk on this graph along the edges such that I traverse such that I touch every corner exactly once. So in terms of the graph, such that I visit every vertex, these black circles, I visit them exactly once. Okay, so very similar sounding to Euler's problem, the problem of Königsberg. It was exactly the same, except that I didn't care about visiting every vertex exactly once. In the previous problem, I cared about visiting every edge or every link or every line exactly once. Okay, that's the only difference. But it turns out that that makes a world of difference to this question of whether the problem is intrinsically hard or is it intrinsically easy. So what exactly is hard about this problem? Why are we saying that this is a hard problem, whereas the problem that Euler solved was easy? So to understand this a little better, let's think of our own game. So this game has two players, and we will call one of these players a prover. Okay, so the way to think about it is that the prover is trying to prove a solution. Okay, whether the solution is that there is a path or there is no path, whatever the solution may be, the prover is trying to prove a solution. So we'll think of the prover as God. Okay, if you care about that analogy. And there's a verifier. Think of verifier as a human being, and they are playing a game. So what is the game? So the goal of the prover is to present a proof that either the Hamiltonian cycle, so this kind of a walk that touches every vertex exactly once. So the prover is trying to present a proof that this does exist or does not exist, as the case may be. So the prover is given one instance, maybe a dodecahedron or some other graph or the map of Königsberg, whatever the graph be. And the prover tries to come up with a proof that either such a cycle exists or such a cycle does not exist. Now, the important thing is we don't care how the prover comes up with the proof. So prover, as I said, is God. So the prover can come up with the proof in any way that the prover wants. We don't even want to think about what the prover has at his or her disposal. Now the prover comes up with this proof somehow from somewhere and presents it to the verifier. Okay, maybe the prover is extremely intelligent like Euler and gives this proof to the verifier. Now the goal of the verifier is to check whether the prover is cheating. Okay, so the verifier just checks the proof and certifies that the prover did indeed prove the existence or the non-existence of a cycle. Okay, so that's the goal of the verifier. The verifier is limited in her role. The verifier just wants to verify the solution. The verifier doesn't want to find the solution. Now this, as I set it up, is rather easy for the problem. So what happens if the Hamiltonian cycle exists? Okay, then what can the prover do? The prover can actually present that cycle as the proof. As I said, it's not of concern to us how the prover comes up with the proof. So the prover somehow comes up with this cycle and just presents it to us, to the verifier. If there is no such cycle, what does the prover do? Well, the prover presents a proof that lists all the cycles, the proof that Euler a long time back said is not such a good proof. But the prover can present this proof, and the verifier can painstakingly go over each of these cycles and verify that none of them satisfy the conditions of the problem. Also verify that the prover has indeed given her all the possible walks on this graph. And that's the end of the story. The verifier is convinced that indeed the prover wasn't cheating. So this problem actually is solvable if in the framework that we have set up. But what's missing from the framework? What's missing is efficiency, right? I haven't insisted that the prover is efficient. In fact, we explicitly said that there is no efficiency restrictions on the prover. The prover can come up with a solution as they wish. But now let us, sorry, this is a typo. So the prover must not be efficient. That's a critically wrong typo. So the verifier must be efficient, okay? So we insist now that the verifier must be efficient. And as we said, efficient means the verifier must run in polynomial time in the size of this graph, in the size of the problem. Now life is a lot harder for the prover, because although the prover can come up with any proof she wants to, now this in the second case where there is no cycle, the prover is out of proofs. Like earlier, the prover was coming up with this long list of all possible cycles. That doesn't work anymore. The verifier just says, I just don't have time to go over all these, right? Give me a short proof, something I can actually read in a short amount of time, in polynomial time. So the verifier must be efficient. Okay, again, not the prover, but the verifier. Let me actually correct this so that we don't get into. Okay, so the verifier must be efficient, not the prover. Okay, so now the proof completely breaks down. And that is what precisely is hard, right? This case where there is no cycle is hard. And in particular, oops, I'll have it on the next slide as well. And in particular, we assert that if P were not equal to NP, then such a prover-verifier combination does not exist. Okay, such a prover and such a verifier do not exist. In the case where there is a Hamiltonian cycle, there's still such a prover-verifier combination, right? The prover can give the cycle, the verifier can verify it. But in the case that it does not exist, there is no prover that can convince an efficient verifier that there is no cycle. And that's at the crux of what is hard about this problem. Okay, so that brings me to the end of the first part of my talk, and I'll pause for a minute to take any questions. The second part is much shorter than the first, so we'll get through this quicker. But if there are any questions, I'll answer them before I go on to the second part. Okay, so I don't see any questions. Arghya, are there any questions on the chat?
No, I don't see any.
Okay.
Guys, you can also type in the questions, or you can unmute yourself and ask. Okay. I don't see any questions as of now.
Okay, all right, let's keep going.
I think there is a question, just how are we relating it to P not equals to NP, the prover and the verifier?
Okay,
this is a question from Shanchita.
Okay, so Shanchita, so if P were, so how is this prover verifier game related to the P versus NP question? So what is the P versus NP question? It's asking, if a problem is verifiable, is it also provable, right? In the sense that if I can verify a proof, or if I can verify a solution, can I also come up with the solution in the first place? Now, if P were equal to NP, so what would the prover and verifier look like? Well, in that case, I claim that I don't need a prover. The prover doesn't need to exist in this world. All that I need is a verifier that simply solves the problem and figures out whether a Hamiltonian cycle exists or does not exist. Okay, so in a world where P equals to NP, I don't need a prover. Just a verifier is sufficient in terms of talking about the problems that I can efficiently solve, or even efficiently verify. But if P is not equal to NP, then the problem is that then I'm assuming that there are these problems like Hamiltonian cycle, where if there were some omniscient prover, some prover that's extremely powerful that could come up with a proof, then I can take a look at that proof and verify that that proof is correct. Okay. So if the prover can come up with a proof to the yes instance, so that's the precise definition of NP, which I didn't actually get into. But the precise definition says that if it's a yes instance, so an instance where there is a Hamiltonian cycle, then a proof can be verified in efficient time. Okay, so in particular, this problem Hamiltonian cycle is in NP. However, it's not in P. So that prover that comes up with that solution, that original solution is required. If I take that guy away, then the verifier on its own can't solve the problem. Okay, and one particular connotation of that is that in the no instance, so in the counterpart of the yes instance, in the opposite case, so in the case where you do not have a Hamiltonian cycle, there, even if a prover, there is no way for a prover to convince a restricted verifier, an efficient verifier, that there is such a solution, that there is, that you do not have a solution. Okay, so this class, so I didn't want to get into more details. So this class of problems where in the no cases, a prover can convince the verifier, this class of problems is called co-NP. Okay, so the class of problems where the prover can convince a verifier in the yes case, these are called NP. The class of problems where the prover can convince the verifier in the no case, these are called co-NP. And if NP and if P is not equal to NP, then we know that Hamiltonian cycle is one of these problems that's in P but not in co-NP. Okay, so that's why if P is not equal to NP, then we know that the second bullet cannot be done. So you there is no prover that can convince an efficient verifier of a no instance, that there is no Hamiltonian cycle. Okay, so this goes a little deeper than what we have seen here, but this goes into this idea of one of these bullets being NP, the other bullet being co-NP, and all these problems that we think of as really hard, but are in NP, as we saw for Hamiltonian cycle, these problems cannot be in co-NP. Okay, if they were, then NP and P would collapse and would be equal. Does that answer your question, Sanchita, or do you want some more explanation? Okay, all right. Let's keep going, and I can try to explain a little more at the end if you have time. All right, so let's move on to the second part of trying to come up with universal theorems or universal theories. Okay, and again, let's start off by trying to understand what a universal theory means. So theoretical physicists, particularly in the 20th century, have really grappled with this question of coming up with a grand unified theory of the physical world. And this question arises because now all of us know that the macroscopic world, the macroscopic physical phenomena, are governed by the general theory of relativity. The microscopic theory, physical phenomena are governed by quantum mechanics. But there is these two theories, that of the general theory of relativity and quantum mechanics, seem to be at logical counter, like at loggerheads with each other from a logical point of view. And there is no single theory that explains both the microscopic physical world and the macroscopic physical world. And really, theoretical physicists have really grappled with this question. Again, a very sort of a question that's seeking to unify our understanding of the world. Similarly, in biology, Darwin, when he wrote this his famous book, The Origin of Species, asked, is there a unified theory of evolution for all life forms? So not just for, so for example, is there a theory of evolution for flowers, for plants? And somehow his theory of evolution that was based on his theory of evolution for human beings and other animals didn't quite translate to botany. And he in fact called this the abominable mystery of evolution. So again, the quest for a unified theory, a single theory of evolution that explains every life form. And something that we are going to talk about quite a lot is the theory of a unified view of mathematics, right? So in 1900, David Hilbert, who was perhaps the more preeminent mathematician of his time, so he gave a talk at the International Congress of Mathematicians, where he listed 24 problems that he called the challenges for us mathematicians. Okay, so Hilbert's 24 problems has since become a very famous benchmark for what are difficult mathematical questions. And among them was one problem, the 10th problem, that talked about something that eventually got translated into the desire for a unified axiomatic structure of mathematics. So what does all of mathematics rest on? And that's a question that we are going to explore in far greater detail. Okay, so what are the foundations of mathematics? Let's try to understand that, because that is what essentially led to the birth of computer science. So in the sort of older times, actually till the middle of the 19th century, mathematicians didn't actually explicitly think of this question. Is there a foundation on which all of mathematics rests? So the first sort of stab at this question was by the German mathematician Georg Cantor in the second half of the 19th century, so 1850s, 1860s. So he set the role bowling on trying to explain the foundations by introducing what's now a very popular theory called set theory. So he said that, look, all of mathematics rests on this idea called sets. And we will see a lot more of this idea, because that's what also computer scientists talk about. And in the process, so this is a little bit of an aside, but in the process of introducing his set theory, he took on a lot of different groups of vested interests. So he took on religion, and we'll see why, and tradition. And he also took on a lot of his own peers. So a lot of mathematicians of the day were very dismissive of him, dismissive to the extent that actually hurt Cantor. And Cantor sort of slipped in and out of depression for almost the last 20 years of his life, partly because of this kind of completely nonsensical criticism that he took. Now, why was he being criticized so much? So he was criticized because his main sort of driving goal, or his driving objective in defining set theory, was to understand the meaning of infinity. So till this point, so we have a lot of things are in our universe around us, in the world that we are familiar with, that are finite. So people understood finiteness pretty well. But what is infinite? Now, already, like people like Leibniz, who came up with the idea of limits and calculus, were already sort of hinting at that finiteness is not enough to describe everything, right? Finiteness is limited. So they were already hinting at infinity, and then theologians were okay with that. They said that, well, finiteness is the world around us. Infinity is God. That's what religion says. God is infinite. But what Cantor showed is that infinity is not this one thing that exists, but there are different kinds of infinity, and not all infinities are equal. Like there are small infinities and large infinities and countable infinities and uncountable infinities, and lots of different types of infinities. And that really, really caused problem, because now he was basically saying at least that was the interpretation for many people in religion, that he's talking about multiple gods, and that in 19th century Europe didn't go down very well. So he took a lot of criticism, and we are glad today that he stuck to his theory. But in some sense, his theory of sets was somewhat naive. Okay, so here's how it was naive. So this is something called Russell's paradox, and we will connect it back to Cantor's set theory. But let me ask you a sort of standalone question for now. So think of the following. So suppose there's a village where a barber shaves all men in the village who do not shave themselves. Seems perfectly normal, like perfectly fine definition. There's just a one barber, so the barber shaves everyone who doesn't shave themselves. But then who shaves the barber? So let's try to understand this. So if the barber were to shave himself, then by definition, he doesn't shave himself. On the other hand, if the barber were not to shave himself, then by definition, he should be shaving himself. So this definition that I have written for the set of people that the barber shaves is extremely problematic because we don't really know who shaves the barber. Now, Bertrand Russell, one of the greatest logicians of the 19th century, so came up with a sort of more formal way of stating this paradox. So Cantor had said that a set is a collection of objects, perhaps the most natural way to talk about mathematics. So here's a set. What's a set? It's just a collection of objects. It could be finite, infinite, but it's a collection of objects. So Russell said, all right, so if it's a collection of objects, let me define such a collection. So let me define a set that contains all sets that do not contain themselves. Okay, so for every set, it's a collection of objects. Among those objects could be the set itself. So let me mark all these sets that do not contain themselves. And let me dump those sets into a single set. So that's a set I have defined. It's a set that contains every set that does not contain itself. Now the question is, does the set contain itself? That set that I have now come up with, does it contain itself? And again, you run into this paradox. Suppose the set did contain itself, but then by definition, the way that I have defined the set, it shouldn't be containing itself. On the other hand, if it does not contain itself, by its own definition, it should be containing itself. So we get into this exactly the same paradox that I stated informally via the tale of a barber. And that's told mathematicians that something is awfully, awfully wrong. So this led to what is now called the foundational crisis of mathematics. Okay, so the foundational crisis of mathematics needed to be solved. So in the early 20th century, essentially every mathematician worth his or her name was trying to solve this problem because they risked all of mathematics through centuries by not being able to give a proper axiomatic foundation to the subject. And as we discussed a little while earlier, David Hilbert, one of the most influential mathematicians of his time, proposed the ultimate problem, the ultimate unifier. So he called it the decision problem. And my German's not good enough to pronounce that in German. But the decision problem that extended Hilbert's 10th problem that we talked about was defined by Hilbert in the following manner. So he says that the decision problem is solved if one knows a procedure that allows one to decide the validity of a given logical expression by a finite number of operations. Okay, so what does this mean? Let's break this down. So someone gives you some expression. Okay, so what's an expression? So someone says that all primes above 4 are the sum of, all even numbers above 4 are the sum of 2 primes. So that's an expression. Now, if that expression is correct, what Hilbert says is there should be some automatic process, some automatic procedure, which takes in this expression. And if that expression is correct, by a finite number of operations, after a finite number of operations, it can precisely say that the expression is correct. On the other hand, if the expression is wrong, if a conjecture is wrong, after a finite number of operations, this procedure will say your conjecture is wrong. Okay, so what he was really asking for in today's language would be just a computer program. Okay, this program takes in a mathematical theorem, a proposed mathematical theorem, and provides a proof. Either shows that the theorem is true or the theorem is false. Okay, and in finite time. So note the difference between this and what we were talking about in the first part of the talk. There is no notion of efficiency here anymore. So Hilbert's saying this should just be finite time. It can be as long as you want, but it needs to end. It shouldn't be infinite. Then of course you don't get to a decision. And the two sort of key features are completeness. So completeness just means that if the theorem is true, this procedure, this program is capable of proving it. And soundness, if the theorem is false, then this procedure is not capable of proving it. So the procedure will say that it's false. Okay, so it proves every true theorem, and it does not prove any false theorems. Okay, so these are called, usually in logic, we call these completeness and soundness. So Hilbert was asking for this ultimate logical system, this ultimate computer program that is both complete and sound. Now, at the same time, so we will come back to this to Hilbert's question and how the foundational crisis of mathematics got resolved. But let's now sort of let's now shift our focus to something that was happening essentially completely independently, but that would have a very deep impact on this question, and that was the development of computing itself and computing machines. In particular, the notion of a universal computer. So what's a universal computer? So Charles Babbage, who is often called the father of computing, so in 1821, long before any computers existed, so he was poring over some astronomical tables and realized that all these tables had lots of mistakes. Why were there mistakes? Because he realized this is some routine task. So this, as coming up with this table, the entries of the table doesn't need any particular sort of innovativeness. However, it does require care, and it's a laborious routine task. And he noticed that because these tables were sort of calculated by hand, people had committed a lot of mistakes. So in particular, that humans are not always the best at performing these sort of laborious but routine tasks. And he said, I wish to God that these calculations had been executed by steam. So what does executed by steam mean? Well, remember, this is the era after steam engines. So the sort of most advanced machine of the time were steam engines. And so he was basically saying, I wish to God that these calculations had been computed by a machine and not by humans. And he actually followed up on this. So he was, in addition to being a mathematician and philosopher, he was also an electrical engineer and inventor. So he came up with this engine that he called a difference engine. And this was an engine that was actually powered by steam and had all these mechanical components, and the engine was supposed to crunch numbers. Okay, so he came up with this engine to crunch numbers, a computer in the modern sense. And then Ada Lovelace, so Augusta Ada King, who was the Countess of Lovelace, she was also a daughter of Lord Byron, so sometimes she's referred to as Ada Byron. So she realized that there's nothing special about numbers going on here. So she said that it might act upon it, as in the machine, this Babbage's machine, might act upon other things beside numbers. Were those objects, the other things she's talking about, were those objects found to be, were objects found whose mutual fundamental relation, so the mutual fundamental relation between those objects, could be expressed by those of the abstract science of operations. So what is this machine doing? It's just doing a sort of repetitive routine sequence of operations. So Ada Lovelace is saying that, well, there's nothing about numbers here. You come up with any other domain, and as long as that domain can be manipulated and its relationships can be expressed in terms of whatever operations your machine can do, you can solve problems in that domain. And that's how we understand computers today. Almost nobody thinks of computers as a number crunching machine today. We think of these as manipulating strings, for example, and things that are not numbers. So that's what Ada Lovelace came up with, and in fact, she was the first person to come up with a computer program. So she wrote this program for Babbage's machine. By that time, it was called the analytical engine. So she is usually credited to be the first programmer in history. Okay, so but both Babbage and Lovelace were quite a bit ahead of their time. the technology hadn't quite caught up. So although they were doing all this in the early 19th century, nothing really happened for almost 100 years. And then almost 100 years later, suddenly there was a flurry of activity, not so much in building computers, but in coming up with the theoretical abstractions of exactly the same idea. How do I come up with this machine that can compute everything? The idea of universal computers. I can tell it what it has to compute and it will compute it for me. So there were three prominent theories that came up. So Alan Turing, many of you might have seen the movie that that was released on his life a few years back. So he came up with this idea called Turing machines. Alonzo Church came up with lambda calculus, and Stephen Kleene came up with partial recursive functions. Three frameworks for defining abstract machines that can compute everything. Okay, so the goal of the universal computer that Babbage had dreamed of and Ada Lovelace had dreamed of, it was finally coming to fruition, not in terms of an actual machine, but in terms of an abstract concept. And in 1936, Church and Turing came up with what's known as the Church-Turing thesis. Independently, they came up with this. So they came up with it with the following statement. So they showed that if any function is computable, so if I can compute something, I can solve a problem. So think of this as any problem that is solvable, then a Turing machine can solve it. Okay, so if something's solvable, this machine that I gave you can solve it. Okay, and so can all the other formal machines. So lambda calculus, partial recursive functions, both of them could also solve them. In fact, all these they showed were completely equivalent in a precise formal sense. They could solve exactly the same problems in this world, and they couldn't solve exactly the same problems of this world. And the ones they couldn't solve couldn't be solved at all. No one could solve. Okay, so this was really universal computers way before computers were designed. So you have to remember that this was happening at least a decade, probably more, before the first computers came into being. So no computers yet. So the quest for the universal had brought Hilbert's program and Turing machines, or the quest for a universal computer. They had converged to the same fundamental question: what can we solve at all? So Turing had showed that if you can solve something, here's a machine, I have given you some machine that can solve it. And Hilbert had said, well, can you come up with this mechanical way of solving everything, right? So can everything be solved? Can all mathematical theorems be automatically proved? So, and Turing's machines were a way of automatically proving them. So Turing says, well, if you can solve it, I know how to come up with this automatic process for solving it. Here's my Turing machine. And again, to be very sort of careful, we're not talking about efficiency anymore. We're just talking about, can a problem in this world be solved? As basic as that. So that was this sort of big question that the world faced, the world of mathematicians and computer scientists face. And then came incompleteness. Now, I will share my take on this, but let me first say what it means. So Kurt Gödel showed in 1931 that this dream of this logical system that's both sound and complete is infeasible. So he showed that a sound system of logic, so something that doesn't prove wrong theorems, right? Something that can only prove correct theorems. So a sound system of logic cannot prove its own soundness, and therefore is necessarily incomplete. So if you can't prove, it can't prove that it itself is sound. So there's this loopiness, this thing about, we keep saying that we can't quite unravel the mystery of how the brain thinks, because it's our brain trying to think about how it thinks. And this sort of recursion, this loopiness shows up in trying to get a sound and complete system, because it just can't prove its own soundness. Alan Tursky, almost at the same time, showed in what's known as the undefinability theorem that you can't define truth. So if any mathematical system cannot define within the system itself what is true in the system, okay, so the idea of truth transcends mathematical systems. And then Alonzo Church and Alan Turing basically killed Hilbert's program entirely. So, I mean, the thing to remember is Hilbert's program was the preeminent program of the day. Like hundreds of mathematicians across the world were working on it. But Church showed that Hilbert's decision problem, the ultimate problem he had dreamed of, is undecidable. So think of undecidable as just being unsolvable. Okay, so Hilbert's problem is undecidable, and then Turing showed that so Hilbert's problem maybe is this grand vision of a problem. It's not very precisely defined in terms of what we would call a problem today. But Turing gave this very precise problem called the halting problem. We'll see that in the last two slides of the talk. And he showed that this problem, this specific problem itself, is undecidable. So what is this problem? Why do we care so much about it? So here's the problem. The problem is, given a computer program, or you can think of this as a logical system, you can think of this as a geometric system in mathematics, whatever you want to think of this as. But given such a system and given an input to that system, does the program continue indefinitely or does it halt? That's the problem it's asking. So I give you a program, I give you an input. You need to tell me, does the program halt on the input? Now, why do we care so much? This seems like some random problem someone came up with. Why do we care about it so much? Well, the problem is, if the halting problem were decidable, a lot of strange things would happen. Okay, so consider a really difficult problem like Goldberg's conjecture, right? Something that we haven't been able to solve for more than 300 years, almost 400 years now. So remember, this was the conjecture that every even number bigger than 4 is the sum of two prime numbers. So now I have a way of solving this. What do? I write a program, Goldbach, that searches for a counterexample in a systematic fashion. So it looks at every even number, looks at every prime pair of prime numbers and sees if they add up to the even number. So one even number after another, it checks the condition of Goldberg's conjecture. Of course, no one wants to run this program. This will run forever, right? It will never end because even numbers are infinite. However, it doesn't try to run. We don't try to run this program. We just write this program. We can always write this program easily. It will be an infinitely running program if we ran it. But then we take this program and just feed it into halt. This program that solves the halting problem for me. So what will halt say? Halt will say, does this program halt or not? Does it stop or not? Now, if it halts, what does that mean? That means I found a counterexample to Goldberg's conjecture. If it does not halt, then Goldberg's conjecture is true. So all I do is I run the halting program on Goldbach's program as input, and I have solved Goldbach's conjecture. So if the halting problem is decidable, as I said, that would be the end of ingenuity, right? You don't need ingenuity anymore. You can solve all these problems like Goldbach's conjecture that seem really, really hard. You can solve this automatically. You don't need any ingenuity at all. But the halting problem is undecidable, as Turing showed. And this is my last slide. So I couldn't resist putting in a proof because the proof is beautiful. And the proof requires less than one sentence. But before I prove that, I want to say that the reaction of the mathematical world of the day to the fact that there were these problems that you could not solve, the world had problems you could not solve automatically, the reaction generally was negative, right? So Hilbert's program had collapsed. People didn't know how to think about that. So because they were very hopeful that Hilbert's program will come up with this sort of automatic way of obtaining theorems. But in hindsight today, we find it liberating, right? Because as I have insisted, these results that show that we are limited, that we cannot come up with a system that automatically solves every problem, that has ensured that our that sort of human creativity remains an important factor in the game. Okay, so you can think of this as a very liberating thought. Okay, so let's think of the halting problem. And the way Turing showed that this is undecidable is just going back to Russell's paradox. So here's what he did. So he says that define a new program. So I know that there's a halting program that decides whether you can halt on an input. But now let's decide a new program called no halt. So this program takes as some input, let's call that x, and then it halts if and only if x does not halt on itself. So remember that I can decide, assume that I can decide, we are assuming that halting problem is decidable. So I can decide if x halts on itself, right? That's just a halting problem. So I figure out if x halts on itself. If x does halt on itself, I just go into an infinite loop. If x does not halt on itself, I say, okay, it doesn't halt on itself, let me stop. So no halt halts precisely if x does not halt on itself. And the question you now ask is, does no halt halt on no halt? So I take this program no halt, feed it no halt itself. Okay. Now, if no halt were to halt on no halt, then by the definition of no halt, it means that x does not halt on itself. But what is x? X is no halt itself. So no halt does not halt on itself. But then that's a contradiction, right? I started off assuming that it does halt. Now, let's look at the other case. Suppose no halt does not halt on itself. But that means that x does halt on itself. But what is x? X is no halt. So that means no halt does halt on itself. Again, a contradiction. So we are back to Russell's paradox. So if the halting problem was decidable, then I could also write a program called no halt, and no halt leads to this paradox. So the only solution to this is that the halting problem is not decidable. All right, so that's all I have today. So I just want to end with a very quick slide of caveats. So what you saw today it's certainly part of computer science, but by no means all of it. And there are vast areas of computer science that we didn't discuss that also exhibit some of the same features that we did discuss. So it also asks fundamental questions, and it also seeks to unify. And in fact, our discussion didn't even touch on all aspects of the theoretical parts of computer science. In specifically, it almost had nothing to do with what I do on a day-to-day basis. I'm a theoretical computer scientist, but I usually, my work is more in the area of trying to figure out for problems that you can solve efficiently, how do you solve them efficiently? And for problems that we can't, how do you get around this fact that we can't? What can we do? And in particular, we didn't talk about anything that has happened in the last 50 years in computer science, the so-called golden age of computer science. But still, I hope that I have convinced you that there's something brewing here. There's something beautiful. There's something interesting. There's something worth studying in computer science. And with that, I'll stop and take questions.
Thank you so much. Thank you so much for bringing all these very fundamental problems and presenting in such a manner. As we wait for the questions, maybe someone would unmute and ask, or put them in the chat. I can read them out if you put it in the chat.
And just to be clear, so I am happy to answer questions. Arghya specifically also asked me for this, but and I certainly want to do this. I am happy to answer any questions about anything not related to the talk. So if you want to ask me about a career in computer science or anything of that sort, I can try to answer that to the best of my ability. So feel free to ask me any questions, particularly, like, it seems like many of you here are currently students. So if you have questions that have nothing to do with this talk, but you would like me to give you my opinion, I would be happy to.
So here is the first question from Arghya. In the Hamiltonian cycle problem, if the prover says that there is no solution and there is no efficient way for the verifier to verify it in polynomial time, because it will take exponential time to exhaust all the possible combinations. Is it so? Is the statement true? Is it particularly exponential, or is it even more than that and we don't know?
So if you allowed the verifier exponential time to verify the solution, then indeed you can solve, you can get a prover and verifier combination that does what. So let me go back to the slide. Um, so if you allowed exponential time, then indeed this game is valid. So you, as we said, so if you take away these conditions, then in exponential time, all the prover needs to do is to give you a Hamiltonian cycle if it exists, and give you all possible cycles if the Hamiltonian cycle does not exist. And the verifier can verify both solutions. So if you did not have the restriction of efficiency, then this is solvable. So by no means is this an undecidable problem. Okay, this is very much decidable, but not, we believe that it's not decidable in polynomial time. Now, I want to make it clear that's a belief. We don't know. It's an open problem whether P and NP are equal. If they are, then in fact, you can solve this in polynomial time. And you can get such a game even when the verifier is restricted in terms of how much time it has. But we strongly believe that it's not the case. So we believe that if you don't have, if the verifier is restricted, then there is no prover in the world and no verifier in the world that can achieve these properties.
I also want to ask you if P is not equals to P, as we know, if we can prove it, as you said briefly, that all the secure community or sense of security will go down. I believe the RSA algorithm would not work, right? Which is why every type of secure communication or the cryptography would basically fail. Am I right?
Yeah, not just the RSA algorithm, but pretty much all kinds of what's known as public key cryptography. So where it's not that you and I have something private that we use to communicate, like to encrypt our messages. All kinds of public key cryptography will collapse. So in fact, cryptographers, kind of in their infinite wisdom, have also started talking about cryptography that transcends this assumption. So there is a small part of cryptography that does not rely on this assumption. So they rely on things that are they kind of say that universally, no matter what happens regarding the P versus NP problem, we can encrypt. But that's very limited. You can only do very limited things and also very theoretical things. Almost all of practical cryptography as we know it today would collapse.
I also wanted to ask you something regarding the Hilbert's problem that you mentioned. So is it that Hilbert's problem doesn't have solution for uncountably infinite set, or what happens if the set is countably infinite?
So which specific problem? So okay. So maybe for others, let me put this question in context. So Cantor, we talked about Georg Cantor, and Cantor's one of his sort of biggest legacies is this notion of separating infinities, and in particular, he separated these two different types of infinities. One is called countable infinite sets, as Arghya mentioned. So these are things where you can count infinity. So you say, look, all the integers are infinite, but I can count them. I can say it's 1, 2, 3, 4, etc. On the other hand, there are other kinds of infinities where I can't actually count them. I can't enumerate one after another. For example, all the, let's say, real numbers between 0 and 1. Okay, so I can't say what's the real number after 0. I don't know. What's the one that comes right before 1? We can't come up with this kind of a sequence to count all the numbers between 0 and 1, all the real numbers. So there are these two classes, and of course, even within the uncountable class, there are all kinds of hierarchies. So not all uncountable sets are the same either. But so there are two kinds of infinities. Now, the way that this is related to the discussion that we had is Russell's paradox is in fact a reflection of something called diagonalization. So the way that you show that something is uncountable, at least one of the very standard ways that you show that something is uncountable, is by using an argument called diagonalization. Roughly speaking, the argument is, okay, so I have sets. So sets, I can think of listing all the objects of this world if they are countable. And then I can take a set and I can write the set out as zeros and ones, depending on whether the object appears or does not appear in the set. So in this way, I can list all my sets. The problem is this listing is not complete because I can now look at a diagonal in this matrix of zeros and ones I have created, and this diagonal is not a set I have listed. So actually the diagonal is, but if I flip all the bits of the diagonal from 0 to 1, then that's not listed. So this is usually called diagonalization. It's exactly the same as Russell's paradox. I didn't want to get into the sort of formal proof. And therefore, what basically these people were showing, like all these undecidability results were showing, is that there is this implicit assumption of countability in the things that we can solve. So implicitly or fundamentally, things we can solve are countable, whereas problems we can solve are countable, whereas problems in this world is uncountable. So that's another way of putting this like another way of putting the same thing, that the world of problems is uncountable, the world of problems we can solve or we can decide is countable, and therefore there are a lot of things outside this set that we can't solve. Arko, does that address your question?
Yeah, thank you.
Okay.
We are going a little over time today. I have, in the interest of time, I have a really happy announcement to make from our administrative committee of JBNSTS. If you want to ask some more questions, can you please put that in the chat? If we will try to cover it if we have time. Um, uh, so we are actually, the announcement is regarding our community and broadening our community. Um, we are very pleased to announce that we will be welcoming the Bigyani Konna Medhabritti BKMB scholars in the following week to be the members of the JBSPDF forum for active involvement in the ongoing scientific and professional activities. Bigyani Konna Medhabritti scholarship scheme is an integral part of JBNSTS that encourages the advancement of women in science, technology, and medicine. On behalf of JBSPDF, we acknowledge both senior scholars and BKMB scholars to be the part of the same family and holistically regard them as JB scholars. We delightfully look forward to welcoming our new members. I think some of our new members are in this call also. Um, Firstly, I really want to thank you, all of you, because for being here. I I see Professor Rudro Dotto and Professor Anjon Ghosh, probably they are also in the audience. Thank you so much for joining in this talk. Um,
So, Arghya, I think there was one question that I didn't answer, so let me just quickly address that. So
yeah,
there
yeah.
was a question by Shunchita asking, what is theoretical computer science?
And can I,
Yeah,
sorry, can I also add a little bit to this question?
sure.
Uh, what is theoretical computer science? If you enlighten us a little bit on it, and also, just to motivate the community and all of us, um, what are the traits and things we need to join such a community, and also when, and if you please, why did you want to be a theoretician?
Mhm. Good. So what is theoretical computer science? So very roughly speaking, it is the interplay of computer science and mathematics. So the idea is one part of computer science. So as computer science was being developed as an independent discipline, it essentially came out of two communities. Some of it came out of mathematics, some of it came out of electrical engineering. So the more, let's say, practical parts of computation came out of electrical engineering. Maybe the more theoretical aspects came out of mathematics, and kind of split at some point into a field that we now know as theoretical computer science and a field that we now know as artificial intelligence. So there are these three broad characteristics, three broad categories in computer science nowadays. So there's theory, there's artificial intelligence, and there's systems. And roughly speaking, that's the history of how this came into being. So the part that's like the part that we call theoretical computer science deals with this question of what can we reason about computation as a process, or about the solvability of problems without actually running any programs. So what can we reason about it mathematically? Can we say that we can solve a problem? How fast can we solve that problem? Right? What kind of other resources do we need to solve the problem? If we cannot solve the problem, then how can we show that we cannot do something? Right? It's often a lot harder to show that we cannot do something, as we saw with the Hamiltonian path problem or Hamiltonian cycle problem, right? The fact that we cannot solve a problem is often a much harder thing to convince and prove than the fact that we can solve it, because just showing that you can solve something requires you to provide a solution. So theoretical computer science encompasses all of these, right? So how you can reason about solvability of problems without from using a sort of mathematical framework rather than using, let's say, computer programs, for instance. And how did I get into it, and what's the typical path to become a theoretical computer scientist? Well, I got into it because I like math. So that's a very short answer. So I like math and I like philosophy, and this offers me an opportunity to dabble in these two things as a computer scientist. So that's the very short answer as to why I am interested in it. If you want to if you want to explore this area, I think the best way to do it is through your curriculum. So if you are a computer scientist, perhaps the question you should be asking yourself, and let's say you're an undergrad student, the question you should be asking yourself is, what are those courses that really interest you? If those courses are the ones that are sort of more mathematically oriented, where you do more abstract reasoning, then theoretical computer science might be the thing for you. So that's in a nutshell, I would say that's the test you should apply in order to decide if this is the right thing for you.
There's a last question. So can you enlighten us? So this question is from Bidut Roy. Maybe to generalize the question a little bit, can you enlighten us in the COVID-19 scenario if theoreticians have a big role to play? If yes, then how?
Yes, so they do, as do a lot of other people in other areas. So for example, one of the things, so as you can see, a lot of these predictions that are coming along about what will happen eventually in terms of what fractions of populations will get infected and so on, these predictions essentially are coming out of mathematical models, right? So now the thing about mathematical models is that although you can come up with any model you want, the model needs to be computable, right? If it's not computable, then that model will not be saying anything concrete. You won't be able to say anything concrete about that model for the future. So one of the things that this mathematical modeling is heavily using are algorithms that theoretical computer scientists come up with or have come up with uh, to do things like figure out influence maximization in a network. So think of the following problem. I give you some network. Think of this as the network of people interacting with each other. Uh, Now, the original motivation may be something like, okay, so let's say this is a social network. Who are the people I show an ad to so that they can spread it? Like they can be super spreaders of the ad. And I reach the maximum clientele, the maximum number of people that I can. But in the context of, let's say, COVID, you can rephrase the problem and say, okay, so now I really don't want the super spreaders. So let me try to figure out who are the people I need to give the vaccine to first so that I can slow the spread of the virus, right? Essentially the same question as advertise my new product to a few people so that they can spread it quickly. Okay, and this is something that the theoretical computer scientists, for instance, have worked on for many years now, particularly in the context of ads. But like in the sense that the motivation from this world of like how do I maximize influence. But as is the case often with abstract sciences, uh, what you study for one motivation becomes very important for a different one, and it has become very important for understanding the spreading of viruses.
So maybe geometry, graphs, and curvature. Um, Something
Yeah,
to look forward to.
and the combinatorics of networks.
Combinatorics. Yeah.
And how do random processes work on networks? So that's the sort of crux of the story.
Um, Thank you so much for answering so many of our questions. I know we went over our time a little bit, but it was really interesting to know. Um, Also, so thank you so much. Everyone is basically the chat is a little bit busy. Um, Professor Dotto, you wanted to come in. You wanted to say something. I saw your video on for a little bit.
No, no. I since you mentioned me, I thought I'd take the opportunity to thank Dev Maldo and say that very nice talk. Very direct. As good an exposition of the absolute fundamental mysteries of computing and perhaps everything that I have ever heard. So very much appreciate your talk.
Thank you, Rutger.
Thank you. Thank you, Dr. Dotto.
Okay, all right. Thanks everyone again, and thanks to the organizers. Thank you all. Bye.
Thank you so much, everyone, for being here.